Hello, everyone. It is week 7. We're going to be talking about vectorization and functions. I'm a little bit under the weather, but that's okay. Do we have any questions? I know that I was away last week, but do we have any questions about writing loops and all of that?
I have a quick question.
Yeah, go for it.
I'm wondering if you can clear up like the purpose of pre-allocation and why that is helpful in programming and why it's necessary, and why can't we just write the loop and then assign it to an object? Why do we have to take that step beforehand?
Sure. So basically 2 things about that. One is today we're going to talk about the method I prefer that doesn't require pre-allocation, because I agree that it's kind of like, seems like an extra lift. But 2 is to ensure that your output object is going to be the one that you want. Because sometimes your loop will output like a data frame when you actually wanted a vector or something, and that will hurt you later on. But that's kind of it.
Thank you.
Okay, do we have any other questions? Cool. Let's get started. So we're going to start today with a quick aside. So in virtually any problem you're going to be having while you write code, I would recommend visualizing the goal first. Before you can write effective code, you need to know exactly what you want that code to produce. And I find that a lot of the emails that I receive, like looking for little troubleshooting things, is a lack of clarity about specifically what someone wants to accomplish by the end of their code. So here's some questions I think that can orient you towards ensuring that you know what your goals are first. So do I want a single value, a vector, or a list? What level do I want my observations to be at? Do I want them to be per person? Do I want them to be person year, just the state, that kind of thing? I would argue that most programming problems can be reduced to having an unclear idea of your end goal, or sometimes an unclear idea of your beginning state. So if you want to know if you know what you have, i.e. the data structure, and what you want, the intermediate steps are usually obvious, and troubleshooting that part can normally be constructed in like a quick Google or a quick Slack message to Brian. When in doubt, sketch the beginning state and the intended end state. Then consider what translates the former into the latter in the least complicated way. And if that seems complex, oh my goodness, I am not very professional. My bad, my phone went off. If that seems complex, break it into more steps. And I have a picture here of one such thing. This was during a project I was working on, I don't know, maybe 6 months ago. And the idea was I was interested in the mortality and the longevity of businesses that open up in different types of gentrifying areas. Okay, so like what kinds of industries were really trying to take advantage of gentrification to make money. And what I had was a data set that was all of these birthdays and death days of businesses. And then I had a different data set that was per year information at the business level of information about the business. So like how many people they employed, an estimate of how much money they make, an estimate of the kind of industry they were in, and whether or not they were part of some big conglomerate or mom and pop and that kind of thing. And so what I needed to do was join those 2 sets of information together. And I sketched it out like this. So I have the birthdays, but what I need them to be is a business year for each row, so that I can left join it to the employment data that is captured at the middle of a year. And so the first thing I did was get a distance from the start date to the end date in years, and then make a data frame per business that is the amount of rows would be the amount of years that the business was alive, or all the way through the end of the data set if it survived to the end. And then I would make a list, which with each element would be a business. So there'd be data frames in every element of the list. And then I would bind them all together so that I would have this really, really giant data set that was a business year for each business in my data set that I had a birth date for. And then I would iterate over those dates in the whole bound data set. And then I would subset to the year in order to left join my employment data that was, again, captured at the middle of the year each year. And then I would concatenate all of those in order to have information to run a really large event history model on the survival of all of these businesses, conditional on things like how many people they employed and their gentrifying area status. But that started from just this kind of sketch. Okay, let's talk about vectorization. So recall from last week, remember when we tried to find the mean for each variable in the Swiss data set? The best solution is to use the col_means function without even thinking about pre-allocation or for loops whatsoever. It's way faster and way easier to just say col_means my data frame, and it will give us the column means of each of the columns, right? And so what I want to motivate for this week is how can we leverage this kind of structure so that we can avoid loops as much as possible, because writing them is kind of a hassle, and these were a lot faster. So reasons that I would prefer a vectorized function over a loop. While loops are very powerful and applicable in almost any situation, kind of anything that you'd want to do in R where you'd have to do it more than once, you could write a loop for it if you'd like, although that would be very time consuming. They're often slower and require writing more code than a vectorized command. So we're going to be writing even less code. So recall I was talking about writing loops means you have to write less code than if you had to write each iteration separately and do all the assignments each time. Writing functions yourself will require even less writing than writing for loops. Whenever possible, using existing vectorized commands like col_means or dplyr functions is way faster and only requires that you remember what the names of them are typically. And it's really easy to find examples of people using them in various contexts. Sometimes no functions will exist for what you need to do. And so you'll be tempted to write a loop. And I would argue that this makes sense on a fast one-time operation on small data. So like if you are just trying to clean a data set in order to run a bunch of analyses later, and you're not terribly worried about doing that cleaning again, doing that cleaning on a second data set, sometimes the first intuition you'll have about writing a loop should be the one you use. However, if your data are large or you're going to do it repeatedly, consider writing your own functions. And this will offer the kind of flexibility and pliability that you might need if you're going to be doing things on large sets of data, things that go slowly, and times you will need to run a similar operation a bunch of times. Okay, writing functions. So some examples of existing functions. I'm presenting these here to offer a sense of how these work sort of mechanically so that when we write our own, they are not as scary. So the mean function provides the arithmetic mean of a vector. So the input is a vector and the output is a single number, right? when we use the dplyr filter function, the input is a data frame and one or more logical condition, and the output is a data frame with rows removed using those conditions. That's tracking, I'm hoping. And then the read CSV function, the input is a file path, and optionally things like the variable names or the types. Remember the week 5, I showed you like the lowercase I and C and C and C and capital D and all that to coerce the row types, column types. The output is just a data frame containing info that's read in from some other file somewhere. So why would you want to write your own functions when there's really nice things like read CSV and what have you available? Functions can encapsulate actions you might perform often, such as given a particular vector, compute some special summary statistics. Perhaps you're like me and you don't really like R squared and you would like some other kind of model fitting statistic to be run. Perhaps given a vector and a definition of invalid values, you might want to replace NAs in your data set. Perhaps you have a really strong inclination toward some particular look of a ggplot, and you would like all of your plots to look that way and all of your papers for all of your life. You can write a little template for that. Or perhaps you'd like to make your own logical operator. You don't really like the way that the modulo returns remainders, that kind of thing. Some advanced function applications that are not going to be covered in this class, but you could ask me about them, would be parallel processing. And parallel processing is, okay, so like when you run R is only running on one core of your computer. So it can't, so you're not really leveraging all of the possible power that your computer has. So like the computer that I am zooming on right now has, I think, 6 cores. I could, if I asked it to, run a particular procedure on each of the cores so that it would run some big operation a lot faster than just using one core, like an instance in R would. And this is what makes using the CSD sim cluster really nice, is you can ask to use like 120 or something. I don't know how many. Don't tell Phil Hurwitz that I have just been allocating cores to the sim cluster to do things from time to time. Other advanced function applications, you might want to generate other functions within using a particular function. That might not sound like something you would need right now, but perhaps you have like a dashboard or an application or something that needs to run some very complex operation after somebody has specified what you want it to do. So you can have the function take their options on their end of the dashboard and then create a function to do what they're asking it to do. And lastly, making custom packages containing your functions. So you could write your own package that just includes all your functions, and you could just run library, Breon's library, and then it will give you all the functions that you already created and like, that kind of thing. They recently updated a lot of the stuff to make custom packages, and it's really nice. Recommend. But T is so good. Okay, let's talk about a simple function. So here is what I would consider a simple function. It takes a vector as its input, and the output's a named vector of just the first and last elements of the input. Okay, so here we assign to first and last. We use the function to make functions. So we say function and then X. So X is going to be the name of our input within the body of our function. And then within the curly brackets, we have the body of our function. So whatever it's going to do is going to be within these curly brackets. And the first thing it's going to do is assign to first our input subset to the first element. And it's going to assign to the last object our input vector subset to the length of our input vector, which will always be the same thing as the number of elements. And then it's going to return a vector where the first thing is going to be named first, and it is going to be our object. So is this first object. And the second thing is going to be last, and it is going to be our last object. So let's see how it looks. We're going to test it out on a vector with the elements 4, 3, 1, and 8. And first and last will return first, the number 4, our first element, and last, the number 8, our last element. Are we tracking there? We're cool with what's going on here thus far? So let's test it a little bit. I highly recommend doing this whenever you write your own functions. See whether the use cases for it breaking. What if I gave first and last a vector of length 1? So it will return to us the first element of the vector and the last element of the vector, which here is the same thing, kind of like I'm my mom's least favorite son. And what if we had a vector of length 0? It's going to return an NA. And this might be like a curious situation, but if you return back to the function and how it works, we can't subset to a 0th element in R. Things start on the number 1 in R. So it's going to give us back an NA. And it's not even going to compute the last thing. Since it's an NA, it's broken. It's done. So maybe we want something that's a little bit smarter that can handle some of these sort of edge cases of vectors with interesting qualities. So first, let's make sure we get an error message when the vector is too small. So here we're going to assign to the smarter first and last function, our function. It's going to take x as its input. And now we're going to say if the length of our input vector, x, equals 0. Here I'm using the L to specify an integer 0. You don't have to do this, but if it equals 0, stop. And the stop function here is going to keep our function from continuing to run and then provide a message that we input inside the stop function. So here we're going to say the input has no length, exclamation point. And then we're going to say else. So we have this if else structure. And then our function as is from before. Okay. And now when we say smarter first and last, numeric vector with the length 0, it will return to us error and smarter first and last. The input has no length. And if we say smarter first and last 4, 3, 1, 8, it will return the same 4 and 8 like we suspect. So pretty much all of the, I might have said this last week, but pretty much all of the functions that you tend to use that provide some sort of cryptic error message, someone wrote something like this. Someone wrote an if else that looks like this within the body of the function. And if it was a very cryptic error message, it probably was because they didn't know exactly how it was going to handle your edge case, or they did not take the time to write a good error message like this. If you type a function name without any parentheses or arguments, you can see its contents. So if we look at smarter first and last, and we don't have like any parentheses or anything on it, it will return just what the function does. You can also put your cursor over a function and just hit F2. And so that way you can check and see how a function is handling your data, maybe particularly because you got some sort of error. That actually reminds me, we should check something real quick. Okay, if we do, let's say, dplyr. Okay, and now if we do filter with nothing, it won't give us like a really detailed description of what's going on here, right? It'll just say like function takes these arguments, dot data, some stuff. This argument is already handled for us. And it just says use method filter. If you want to see how things under that, like what use method means, you can actually say like dplyr and then use 3 colons and then say filter and do like filter.dataframe, and it will tell you more about what it does. That's because often is the case when there is a sort of top level function, it is calling other functions that are housed someplace else in order to run. And those are really complex and are taking lots of different arguments and trying to account for all sorts of different problems. And so those are just described as like use method, whatever. But you can look at them if you'd like and just keep going down the like rabbit hole of what does dplyr row slice do? What does filter underscore rows do? Et cetera, et cetera, et cetera. This is often good if you have some sort of really weird use case of, I don't know, a likelihood estimation that's not handling your zero inflation or something. Anyways, and it's also the reason that some of the packages require you to download other packages and install other packages is because their like use method filter requires a function that's in a different package, and they didn't want to just port it over. They would rather just call that other package. Anyways, the anatomy of a function. So this is how your functions are going to look, more or less. First, you're going to assign the name of the function. You're going to assign to that the function with an argument. This argument 1 is typically a whatever your input is going to be. Argument 2 is typically some other input that you can or you may or may not be setting a default answer for. Then the body of the function, so what's going to happen, and then you're going to return the output. So here, the name is what you assign the function to, so you can use it later. You can also have anonymous functions, that is, functions that don't have a name. They just start from this part. I'll show you an example of that in, I don't know, half an hour. The arguments, so the inputs, sometimes called parameters, these are things that the user passes to the function that affect how it works. So things like x or na.remove in my new function, we'll take the function, x will be the first input, then na.remove equals false. So na.remove equals false here is an example of setting a default value. If the user doesn't say what na.remove is, it'll just default to false, right? Which we've seen before in our summarize mean or summarize median. One important thing to note is that your x and your na.remove objects, while they are going to exist within the body of the function while the function is running, they do not exist in or outside of that function. So they're not going to show up in your environment the same way that objects that get assigned within a for loop will exist in your environment outside of the operation. The body will be the actual operations inside the function, and the return value specified by the return function is the output inside return. It could be a vector or a list or a data frame or another function or even nothing. If it's unspecified, the function will return the last thing that was calculated. And sometimes this is not what you want, right? Like if we had let that first and last function go and did not specify a return, it would have just given us back the last part. So you want to say return and the express thing that you want output. Otherwise, you are just being implying that you want whatever the last thing that was assigned or calculated. So an example, let's talk about reporting quantiles and summarizing statistics that are not built into the summary function to start. So maybe we want some quantiles that have interpretable names. Here's a starting point. So we'll make a function that takes an input we're going to call x, and then we're going to say that it's not going to, or it's going to default na.remove to false. And then within the body of our function, we're going to assign to quants the quantile function with our vector input. Our na.remove is going to be equal to the na.remove that the function user specifies. So if they don't change this to anything else, this is going to say false. And then the probabilities that we want in our quantile function are 1%, 5%, 10%, 25, 50, 75, 90, 95, and 99. And then we're going to assign to the names of this quant vector interpretable names for each of our quantiles of interest. And then we're going to return our quants vector. And now we're going to run our quantile report function on 10,000 draws of a random normal distribution with mean 0 and standard deviation 1. And we get pretty sensible results. The bottom 1% is negative 2.3 standard deviations to the left of 0. Our top 1% is 2.24 standard deviations up from 0. Our median is basically 0. I think we did pretty good. Do we have any questions here before we go on to talking about apply functions? Okay, let's move on. So an aside on apply functions. So don't loop, apply yourself instead. Writing loops is challenging, particularly for new coders, which is why I tried not to have too many questions in the homework about loops. So loops also require writing a lot of code and can be hard to troubleshoot. I know a lot of folks have a lot of issues saying like, okay, I put I up here, but I don't know how I gets to be down here and where does it go? And how do I know it's taking on these values, that kind of thing. But loops aren't the only way that you can iterate over things in R. Like a loop, apply functions iterate over elements of an object, except they don't need pre-allocation. You can directly assign the output and it will assign the output to a object that you specify within the apply function. Also, they must use a function. So like in a loop, you don't have to use any functions in order to get it to run, but applies do require a function. Nearly anything you can do with an explicit loop can be done more easily with the apply family of functions. I do want to note that I'm going to be describing how the apply functions work, but there is a tidyverse version of apply functions that's called per. You might have seen them before. They're trying to think about what's the main name. Map, the map function, map DFR, map DFC, that kind of stuff are in the per package. They have a lot of options for being more explicit about how things are going to iterate than the base R apply functions. But I'm going to be describing the base apply functions in part so that you get a some experience seeing how they work, because they're so portable to other languages, and also so that you can have some practice in being very explicit about what you're going to iterate over. Whereas per can make that, I think, a little bit almost too user-friendly, such that you can make a lot of mistakes and it will still run. Okay, so first, I'd say the one I use most often is lapply. L here stands for list. So list apply these functions. Lapply is used to apply a function over a list of any kind. A data frame counts as a list, and it will also return back a list. So this is a lot easier than preparing a for loop. I recall saying, like, I don't like that in order to pre-allocate a list, you have to use the vector function. That's very confusing to me. lapply makes it very easy. I can just say lapply to the Swiss data set, and our function is going to be our quantile report function, and it will just, boom, go and make a list with each element is a column in our Swiss data set, and it will run our quantile report on each column.
So what is the list here? Is that Swiss?
The list that was sent, like, yeah, so the list is the Swiss data set.
Okay.
And since data frames count as lists, you can use lapply on data frames.
Oh, okay, got it. Thanks.
Of course, and it'll iterate over the columns. There's also sapply. So a downside to lapply is that lists are hard to work with. I don't really like working with lists. When I can work with something else, a data frame or a vector, I tend to want to. Sapply, S here stands for simplify, simplifies the output by making each element a column in a matrix. That's the usual case. So it'll look something like this. If we sapply for our Swiss data set, our function here, quantile report, it'll now make this matrix with named rows of each of our quantile report things, and each cell here, like our 1-1 cell, is 38.588, the bottom 1% of the fertility column. There's also just the apply function, which works over matrices or data frames. You can apply a function to each row. Here you specify which direction you would like it to iterate over. So margin equals 1 will be the row, margin equals 2 is the column. I'm trying to recall right now what margin equals 3 does. It's not coming to me. I'm pretty sure that it goes backwards, like it would work with an array, and it would go that third dimension in depth, but don't quote me on that. So here we can apply to the Swiss data set, margin equals 2 for a column, and our function will still be the quantile report, and we'll get the same thing as the sapply. So here's what I'm saying. You can be kind of explicit about whether or not you want to iterate over rows or columns by specifying the margin. Whereas in per, you would have to say something like map underscore data frame C, and that will do data frame columns. Perhaps you recall the loop for loading data files from last week. So here, what happened was we loaded the dplyr package and the reader package. We made a file list for all the files that were in our working directory in the example data folder. We pasted together those file lists with the paths. We removed the CSV part of the file path. We allocated a list vector, or we used the vector function to allocate a list that was the same length as our file list. We wrote names using the names without the CSV of the file path to our data list that we had pre-allocated. And then we said for each item in our file list as a number, subset our data list to that particular number, and then read CSV at the file path at that same element location. And then we took that complete data and we bound those rows together and we got this. And I don't like writing code this way. It's a little convoluted. So what we can do instead is use lapply. We could just say assign to the complete data, lapply our file paths, and use the read CSV function, and then bind the rows. And boom, it's done. Didn't have to pre-allocate. We just had to know where the file paths are. So we only had to do this part. We can actually do this part quicker by just making sure our list files gets to this thing to start. And that's that. So this is why I'm trying to motivate that vectorizing things is just like way easier. It's way easier on my brain than doing all of this stuff every time. Alternatively, you can just say, use the vroom package. So then you could just say assign to the complete data object vroom the file paths, and it will just do this step for you. It skips this part, it does that for you. And you don't have to tell it read CSV. It's pretty nice. Okay. So one question you might have is, okay, I'm like I think applies are cool. How do I go from writing a loop, which I feel like I have a pretty good intuition about, to getting things to work as an apply? How do I get a function to do the iterative part? Sorry. So to convert a code in a loop to an apply function, I think it's pretty straightforward. What you iterate over in the loop, something like sequence along X, will become the first input. The body of the loop becomes a function. This function should take only the iterator index as an input, and then assign the output to what your loop stored values in. Okay. So something like this. We have this loop. We assign to the loop vector a numeric vector length 5. And then we say for X in sequence along our loop vector, assign to loop vector at each element X squared. And then our loop vector will say, we'll have elements 1, 4, 9, 16, 25. So sequence along loop vec here is just the numbers 1 through 5, but we did need an empty loop vec to store these results. Alternatively, what we can do is say this, assign to the apply vector, sapply for the numbers 1 through 5, function x, x squared. and it will give us the same results. So to go back to what we were talking about, so what you're going to iterate over in the loop becomes the first input. So here, we're going to iterate over the numbers 1 through 5. That's what sequence along loopback is doing. So that's going to be our input. The body of the loop becomes a function. The function should take only the iterator index as an input. So the body of the loop here is, we only need this part because the assignment gets done at this stage here. So the body of our function is just x squared. And then assign the output to what your loop stored values in. So instead of having to assign to here, we assign out here. So for apply functions, we don't need to pre-allocate. We just sapply over 1 through 5 directly. This scales up. If you can write a loop, you can convert it to an apply in the same way. One thing to note is that this is an anonymous function that I've written here, is that it doesn't have a name. I just said function x and then x squared. And sapply knows that x here means each iteration of our input here is going to become calculated using this function and is going to get sent back to this object. Okay. So back to making and using functions. I'm actually going to say, let's take a 5-minute break here. And I'll see y'all at 4:18. All right. Back to making and using functions. So here's an example. Perhaps we want to discretize some continuous data. Maybe you often want to bucket variables in your data into groups based on quantiles, like you read Chetty et al., for instance. Am I recording? I am recording. Yeah. Okay. Yeah, so you want to discretize your data, like Chetty and them. And you want to make a function to do it for you. So there's already a function that will do something similar. It's called cut, but you need to tell it where the breaks are, aka like the number of buckets. So let's make a function that calls cut and then uses quantiles for splitting and returning integers. Okay. So our function is going to take an input called x, and then we're going to, it's also going to take an argument for its quantiles, its quants, and the default's going to be add 1/3 and 2/3 in the data set. And then within the body of the function, we're going to assign to new breaks a vector where the first element is going to be the minimum element of the vector minus 1. Then the output of the quantile function for our vector. And our probs are going to be the argument that gets passed up here. And then the last element of the vector is going to be the maximum number in the vector plus 1. And it's going to return the cut function for our input vector. And its breaks are going to be this new breaks vector that we've created here. And it's not going to have labels. Okay, so what's going on here is we're taking this vector of some numbers, Then we're going to set extreme values for the lowest and the highest one. So whatever our lowest value is, -1, and then our quantiles of interest, and then whatever our highest value is, +1. Okay, does that make sense for how we're making these buckets? That makes sure that it captures all of the information that we want in each bucket. Okay. So by default, this will produce 3 buckets. Anything below the 33rd percentile, and note that our bucket will be large enough to get anything, even our lowest value -1, so it's like sufficiently large. Anything between the 33rd and 66.7th percentile, using our quantile function and the quant argument that was passed, and then anything above the 66.7th percentile. And to capture all those high and low values, we started with the min x-1, because you might cut out the lowest number if there are a bunch of them. So if our vector had like 4 1s in it, then we might only get one of those 1s in our bucket. Whereas if we had its lowest number be 0, then we'll make sure to capture all of the ones that are equal to our minimum. Of course. So let's try out our bucket function. We're going to generate some data using a random normal distribution with mean 0 and standard deviation 1. We're going to make 100 draws from that and call it DAT. Our DAT quants that we're interested in are the 5th percentile, 25th, 50th, 75th, and 95th. And then our bucketed DAT is going to be our bucket function using that DAT that we made from our random draws. And the quants that we're going to pass are our DAT quants. So we're going to pass these quantiles in order to create each of our buckets. And then we're going to plot them in order to see that we did a good enough job. And so here I've used the base plot function to just on the x-axis make the bucketed DAT. On the y-axis are data. And this is governing how big the dots are. And this is governing where all of the lines are for our buckets. So things in the 5th percentile are here. Things in the 25th percentile and not in the 5th percentile are here, and so on and so on and so on. But this was an example to help motivate that you can use functions from elsewhere in the function that you make in order to get it to do what you like. And also a plug for if you're doing some sort of operation on your data like this, it's often good to plot it to check where all of your cases are going. So another example would be removing bad data. So let's say we have data where impossible values occur, right? So we're going to make a school data frame. We're going to assign to it a data.frame. School is going to equal just the first 10 letters of the alphabet as an identifier. We're just fabricating some data for this example. And then we're going to create some probabilities. This is the probability of passing some exam at the end of the semester, or the proportion of students who are passing this exam at the end of the semester. And then the proportion of students who are on free and reduced lunch. Okay. And for those who aren't familiar, free and reduced lunch is often like a really one of our only indicators of how wealthy kids are and how high poverty is in some areas. But let's say we use this data, we would notice that some numbers are not proportions. like -1 here, -13, 99. And sometimes when you get data that you're familiar with, you'll know each of these issues sort of like intuitively, that this data set just tends to call things that are missing, 99. But you might miss something like there's a -1 lurking somewhere. So let's create a function to remove some of these extreme values. So our goal is to be able to input a vector called x. We're going to create a cutoff for the low values and a cutoff for the high values that we're going to pass to this function in order to get rid of them. And then the output is going to be a vector where there's NAs in these extreme places that are past the cutoff. So here's that function. We're going to call it remove extremes. We're going to pass or assign it the function, where x is going to be the input vector. It's going to need an argument for low and an argument for high with no defaults. And then within the body of the function, we'll say x no low is going to be assigned if else x is lower than the low. Supply an NA, otherwise x. And then x no low no high is if else x no low is greater than high. Return NA, otherwise x. And then return x no low no high. Okay, so to back up what we're doing here, it inputs x. Then we make a new vector called x no low that uses an if else function to replace all the values below the low cutoff with an NA. Otherwise, keep that information. And then we do the same thing for the high values, but using this vector we've created over here instead of our original. And then we return the one that's gotten both of the calculations done. And so now we can say remove extremes, our school data, and just our passing exam column, where the low is 0 and the high is 1. And we've gotten rid of these extreme values. But we could also specify what those extreme values are with these arguments, knowing that it was a proportion. So anything below 0 doesn't make sense. Anything above 1 doesn't make sense. Alternatively, we can vectorize using dplyr, particularly with the helper function cross. So the dplyr function across allows us to use a function or apply a function to every variable besides school to update the columns in the school data. Okay, so what's going on here is I take the school data and then mutate across every column except for the school column. So this is like the select. We can just get rid of the operation on the school and just use for every other column. And then we're going to use the tilde here to say, do this. We're going to use the remove extremes function, where x is going to be equal to dot. And dot here is the thing that we're going to iterate over. It's the thing that we're going across, which is all of our columns except for school. And then we supply low equals 0 and high equals 1. And it will change all of our columns that are not the school column using the remove extremes function. And this could vectorize very great amounts of data, right? Like with a laws of proportion in your data set, you could write this one line of code and it would get rid of all of the extremes.
What is the x equal to dot?
So x equals to dot. Remember when we were doing like ggplot and we were saying like data equals dot, or like we wanted to run that linear regression and we had to say data equals dot. So what's happening is across is piping in all of the things we select to the function on the right-hand side. And it needs to know that iterating over all of the columns that it's going to do, where to put them in the function. And so what's going on here is it's saying, take the school data for all the columns that aren't school, one at a time, put them where the dot is, and then run the function, and then return it to its regular place. So like it's saying, take the school data and then use the passing exam column. That's what our dot's going to be. And then run this function and then do it again, but for the free lunch column. So the dot is saying where the iteration is going to happen. Coincidentally, this is a very similar syntax to how the per package works with the tilde and the dot. The tilde telling you which function needs to be run and the dot telling you where the iterative process needs to occur. Okay. So one issue you might run into, well, you would back in the day when I was learning how to do this, was that dplyr uses non-standard evaluation that lets you refer to naked variables. So like you could just say, select without quotes, the fertility column of Swiss. So dplyr verbs like mutate recently started supporting standard evaluation, which is things within quotes, in order to identify columns. So this makes writing functions and loops with dplyr a lot easier now that you can do things like, say, select things with quotes, and then pipe them into a different function. I know this is just a pet example. I'll show you one in a second. You can also skip naming your function within a dplyr chain if you won't use it again. So this code below will return the mean divided by the standard deviation for each variable in the Swiss data set. So here's what's going on. It says take the Swiss data and then summarize across everything. So across every column in the Swiss data set, apply this function mean dot. So dot being the column that we're currently iterating over, divided by the standard deviation of dot, the column that we're currently iterating over, removing all the NAs. And it does this for every column in the data set, one at a time. So now we have the mean is divided by the standard deviation for the fertility column, the agriculture column, the examination column, the education column, Catholic column, and then fit mortality column. Just like that. And we didn't even have to say function X. We can just say tilde, run this operation.
So everything is just a function embedded.
Yes, so this counts as
Okay.
just one function that doesn't have a name. And this can save you typing, basically, since you're not going to be running again whatever the mean of your column divided by your standard deviation of your column is.
Okay. And the everything followed by the parentheses.
Yes, so this is saying across every column. So iterate over all of the columns in the data set that I piped there.
Yeah. So yeah, I guess my question was like everything is just inbuilt as an R function. Like
Yes.
yeah, okay.
You can also use anonymous functions in lapply. But the difference is that you have to use the function part in the beginning. So you'd have to say lapply to the Swiss data set, function X. This is a common syntax is just say function X for whatever your anonymous function is going to consider its input. And then it's the same thing. Mean of X, so our column in our Swiss fertility data set at that iteration, divided by the standard deviation of that column at that iteration. And we'll get the same values. Do we have any questions about anonymous functions? I know they can be a little bit ungangly to a new viewer. Okay. Well, the Slack is open. It's going to stay open. So whenever you run into a problem about how these work, just let me know. I'm going to show now an extended example using ggplot2 so that you can see an example of how to make a template in ggplot2. I actually did this recently. So recall last week, like we didn't have class in person, and because I was getting married, big shouts. But I did have a project for which I had to produce plots. And I had to produce many plots, like probably around 10. Okay. And it had to do with like these, this natural language processing project. And we were interested in the relationships between like 3 of these words at a time. And so I was like, okay, well, I'll just like pick 3 words that are probably of interest to my colleagues and make 10 to a dozen plots with those kinds of combinations of words. Okay. But when I arrived back home, I discovered that my laptop charger was not in my bag. Okay. So I was like, I'm not going to have time to create all of the plots and then email them over, I know, to my colleagues. So Brian, in his great wisdom, said, what if I just made a vector that was all of the permutations of combinations of 3 words in our whole data set, and then made a ggplot template, and then had it make a plot for all of the permutations, and then put them in a folder. And then anyone that they might want would be there for them. Okay, yeah. And I thought this was a great idea. Okay, so I wrote it. My computer dies. But I slept well knowing that like it was populating a folder on the CSD server. Okay. Y'all. That piece of code made 82,000 plots. What in the world? I didn't know it was going to be that many combinations. So I just like, I got to the meeting back on Tuesday morning and said like, yo, how did last week go? They were like, yo, man, you did like so much work. I thought you were off. Anyways, that's the power of vectorization, is that you can be off from work and people will think you just did like 4,000 hours. Anyways, let's look at an example of ggplot2 templates. So let's say you have a particular way that you like your charts. Maybe they look like this. So we're going to use the Gapminder data and ggplot2. I'm going to say ggplot our gapminder data and then filter to a particular country. We're going to choose Afghanistan. And then, excuse me, then the aesthetics are on the x-axis going to be the year. On the y-axis, there's going to be our population in millions. And then we really like the fire brick color, so we're just going to make that our line. It's not going to have an X label because on the x-axis is the year, and people will know what that is. On the Y label is going to be the population in millions, and then the title is going to look like this. And we really like the theme minimal because it's very nice. And we like the text size to be just so. Okay. Now, looking at this, how could we make this flexible for any country? And then, how could we make this flexible for any Gapminder variable? Right, so that you can make, should you so choose, every possible combination of Gapminder variable and country in the data set. So here's an example of what that chart looked like. It is very nice. But if I wanted to make, say, life expectancy in Peru, I would have to change like quite a few things. I would have to change country equals Peru. I would have to change the Y label or the Y mapping. I would have to change the Y label and the title. Excellent. So glad to hear that, Veda. And it would be a lot of work. So let's talk about how to make these things flexible so you can just make as many as you want. So we can have the user input a character string for country as an argument to the function to get subsetting and the title right. So something like this. We'll make a function that takes a country argument, and then within that function is going to be our ggplot. And at the filter stage, our country is going to be equal to the argument that our user has passed to it. And then at the title stage, it's going to say life expectancy in blank, and it's going to be the argument that our user passes to the function. And so now we can make this very flexible by creating a function that just runs a ggplot that takes an argument for our country. So our Gapminder life plot, now when country equals Turkey, it will make this plot. It'll say life expectancy in Turkey and output that information. And then you could say life expectancy in Nigeria by just saying Nigeria here, and it will do that. Pretty neat. Pretty valuable, I'd say. But let's also make the y-axis flexible so that it's not just making the same plots for each country. So let's allow the user to say which variable they want on the y-axis. How can we get the right labels for the axis and the title? We can use a named character vector to serve as a lookup table inside the function. So I know that this looks like a lot of text to write, but when you compare this to individually writing all of the possible combinations, it's way, way more worth it to just write a lookup table like this. So like I said, it is going to be a named character vector. It's going to be a lookup table. So our y-axis label is going to be a vector for each element is going to be named the same thing as our columns in our data set. So like life exp and pop and GDP per capita are going to be the names of the elements of the vector. And then the elements of the vector are going to be what we want the graph to say. So things like life expectancy and population in millions and GDP per capita USD. And then we're going to do the same thing for the title text. So the name of each element of the vector is going to be the column that we're interested in using. And then the content of the element is going to be what we want the text to say. So an example would be, now we can say y-axis label, and then subset to our pop. So our pop column that we're interested in the Gapminder data will now return population in millions. And our title text for pop, when we subset to pop, will be population of blank. Okay. And now we can make this function. So ggplot is usually looking for naked variable names. Recall, because Tidyverse has non-standard evaluation, but we're interested in using standard evaluation in order to use our lookup tables. So we can tell it to take them as quoted strings using the AES_string function instead of the AES aesthetic function that we're used to using in ggplot2. This is very handy for making functions. So now this function is kind of a lot. Let me explain what's going on. We're going to assign to our Gapminder plot function the function. It's going to take two arguments, the country argument and the y variable argument. And then within the body of the function, we're going to have our lookup table. And that lookup table is going to get subset to whatever argument gets passed to our function. And then the same thing is going to happen for our title text. It's going to be subset to the y variable that gets passed in the argument. So we're taking advantage of this syntax in order to get our ggplot to say what we want it to say on the axes and titles. And then we are going to have our same ggplot call. And then our data is going to be our Gapminder data. And then we're going to filter our country is equal to country, which is again passed here in the function call. And then we're going to mutate our pop is going to equal to pop divided by 1,000,000. And the reason that we're doing this here is in part just to motivate that you could, if you want, just at the stage of making your graph, change your data to fit some parameters that you're interested in. So like here, now our pop data is going to be in millions, just like we want. And we're still going to have our cool geom line and fire brick red. And now our GG title is going to be a paste, which just connects strings together, of our title text, which is up here, subset by our y variable that was passed to the argument. And then the country, which is our argument that gets passed up here since 1952 with no X label because it's just the year. And our Y label is going to be our Y-axis label that got subset based on this argument up here. And theme minimal, and we still like our text to be just so. And now we can say things like Gapminder plot, country equals Turkey, Y variable equals pop, and it will create this plot for our population of millions. And we'll say population of Turkey up here at the title. And then we could say Gapminder plot, country equals Nigeria, Y variable equals GDP per capita, and it will create this plot with our correct title and our Y label. It's pretty good. Like I said, it's kind of a little bit of legwork to create these lookup tables. But I think it's worth it if you're going to be making like many plots or going to be revisiting similar plots and or maybe making a dashboard or like a Shiny or something. Yeah. So let's move on to making an operator. So one that I always get questions about and one that I tend to make pretty frequently. Excuse me. Is the opposite of percent and percent. So percent and percent returns true where elements on its left equal any of the elements on the right-hand side. For instance, we will create this vector called US_CA for Canada and the United States. And we'll say Gapminder percent or Gapminder, and then filter country percent and percent, our US and CA vector, and then get the unique or distinct combinations of countries, and then show me the first two. and we have Canada and the United States here. We can invert this to get the opposite. And I didn't show you this before, in part because I think the syntax is convoluted. So what filter actually wants you to do is still use percent and percent, but put an exclamation point before the column on the left-hand side. So they want it to look like this. Take the Gapminder data and then filter not country, percent and percent, your vector, and then yada, yada, yada. Okay, and then we would get things that are not the US and Canada, like Afghanistan and Albania. Okay, I've never liked this. Not column on the left-hand side, percent and percent, my vector on the right-hand side. I think that it's really weird. So what if we wanted to make an operator that does the opposite of this? So we can invert or negate percent and percent to get a not in operator. And the way you would do this is, in order to create an operator, we need to put it in backticks like this. So we say backticks percent not in percent, backticks, and assign it negate with a capital N in backticks, the percent and percent. And that's all you do in order to create your not in operator. So now we can say Gapminder and then filter country percent not in percent USCA, and we'll get this Afghanistan and Albania. And I think that it's so much easier to look at. It makes so much more sense to my brain than saying not country. So negate produces logical negations of functions and will invert the output. You might find that this is going to be useful to you as you write some sort of really complex function later in your life. But I only wanted to show that one so that in the case that you might want to change the modulo or the one that pipes in the formulas for linear regression, that kind of thing. But you can make a lot of different logical operators the same way by putting things in backticks. Okay, so let's wrap up a little bit. Sometimes you may want to debug. Sorry, I play Tekken, and in Tekken there's this move called debug, and they all say it funny, but don't worry about me. I'm just being very nerdy right now. So if something has not worked as you've hoped, you can try to run the debug function on a function, which will show you the world as perceived from inside the function. So you run like debug the Gapminder plot. It'll show you how things work and how you run it. Then when you fix your problem, you can use undebug so that you won't go into debug mode every time you run it. So you can just run this in the console and then run this in the console when you're done. I will say that I've only ever debugged like 2 functions because the functions I write tend to not be very complex. It tends to, my problems in my functions tend to be things like I subset by 0 and it gave me an NA and then it broke my whole function. What happened? And then it makes sense to me later. So I don't necessarily need debug to figure that out. But, you know, good thing to know about. One overview of the whole process is data processing can be very complicated with many valid ways of accomplishing it. I believe the best general approach is the following. Look carefully at the starting data to figure out what you can get from them. Okay, so like what things can you do in order to achieve the goals that you'd like? Determine precisely what you want your end product to look like all the way precisely how many decimal points things are going to have, how specifically you want data to look right at the end. before you do some sort of calculation or something. Identify the individual steps needed to go from step 1 to step 2. So like you saw your starting data and you figured out what you can get to it, but you maybe can't figure out how to get precisely to the end product that you need. Start identifying those steps. And then make each discrete step its own set of functions or function calls. So like you'll recall in the beginning, I had that picture of this chalkboard here, where I needed to say like, okay, I'm going to subset to this particular business. I'm going to make a row per year that it's alive in order to left join it by year to each of the data sets that I have. And then if any step is confusing or complicated, break it into more steps. Okay, so like what I glossed over in my chalkboard example is that I thought I could just skip a bunch of the steps. And it might have seemed convoluted to like make a data frame per business and then add it to a list and then add that list back into a data frame. But it was necessary for the way that I elucidated my complicated steps and to break them up into more. And then next, step 5, complete each step separately and in order. Do not continue until a step is producing what you need for the next step. So that was pretty tough for me when I first started coding, is understanding like, okay, I need to necessarily have this part done before I can go to the next part, or else I'm going to get confused, or things are going to look wrong, or maybe, this is perilous, things will look right, but will have been done incorrectly. And do not worry about combining steps for efficiency until everything works. So until you've like solved the answer one way already, don't go back and try to make things more efficient necessarily. I think this is a place that a lot of people get messed up. So that's why it took me a while before I was able to start really incorporating anonymous functions into things that I did, is because I would just tinker for a while on making a for loop do what I asked it to do. And so understanding how to combine steps at the anonymous function level or writing my own function to handle all of these different problems took me a while. But then once finished, if you need to do this again, convert the prior steps into functions. So I described earlier how to convert like a for loop into a function. Once you can get this part to work, then it's time to go back and make things efficient. And you can just make them all into functions. And now your code will really just shrink in size, and you can just run it all, and it'll take 2 seconds instead of having to check all of the different steps all the way through. One bonus function is that my lectures are rendered with a function. This is the render and print the slides function. So the function takes the week argument, and then in the body of it, what happens is we set a directory for that particular week, which is at a lecture and week, and then the week number. Then I get the current markdown, which is just the week directory plus a subset from that week directory, and anything that starts with these words and ends as a markdown. We're going to talk about what this $sign is doing here, and this asterisk and this caret. I'm not sure if it's next week or the following, but so I get the current markdown, then I render the markdown. So I knit the markdown. It will create an HTML. I then assign that HTML this name and make a PDF of that same name, and then make an R script with a different name. And that R script is going to be the companion that you can use to follow along in class. And then I make the console tell me a message that says the slides are being rendered. It's going to wait about 5 seconds. And then I put my computer to not do anything for 5 seconds while all of this stuff happens in the background. Okay, so sys.sleep 5 says computer stop doing stuff for 5 seconds. This is something that's very useful when you're scraping data off the web. You want to seem like a user, so you don't want to just grab things as fast as possible because your computer will grab them way too fast and crash a website. And then after it's waited 5 seconds, I get a message that says purling slides. And so now Perl is going to take our markdown and output our script companion. So this guy up here. And then we're going to say, make another message called printing from Chrome. And so what that will do is it will render the HTML that our markdown knit in a Chrome instance that is not going to happen on my computer. It will happen in the background. So it's opening up a headless Chrome instance with all of my slides rendered in it, and then takes a picture of them and creates a PDF. So the PDFs you open up on the class website are opened up in a Chrome instance with no head. That does not open up Chrome on my taskbar down here. Takes a picture of each of the slides and then compiles them into a slide deck as a PDF, and then puts them back in that folder and says printing complete. I think it's really neat. And I can hand it a vector too. So I just, when my slides are done that week, I just say render and print slides, and then I put number 7, and then it does all this stuff, and bada boom. So your homework. So your homework for this week is going to use the now defunct Seattle Pronto bike sharing program data. I have provided a template for what I would like you to do. It's a template not unlike the homework 5 part 1 and 2. You have to download the data. It is in a zip document, and you're going to extract that into a folder. Using the provided template, you will write a loop or an lapply. Maybe give an lapply a shot if you got some time. To read in the data from multiple files. And don't just use Vroom. Don't just use Vroom. Try out a loop. You're going to make some functions to clean up the data, and then a function to visualize ridership over the first year. So the first part is due next week. The second part's due in 2 weeks, and that's the last mandatory homework for this class is part 1 and 2. Week 7 or homework 7 is optional. One thing to note is that there is some string processing needed, much of which you have already seen or can probably Google, but some will come in the next lecture. I give suggestions in the template, but I can cover string processing in detail in the lab on Tuesday, if needed before the homework is due. But that's it. Thank you all so much. Oh, thank you.
I have a quick question for you, Brian.
Yeah, go for it.
Yeah, I just got really held up at work, so I couldn't submit the homework yesterday.